On one side, a familiar scene, a vast, sun-drenched field stretching to the horizon. A diesel truck kicks up dust, a symbol of the immense logistical chain that brings food from these fields to our tables. This is agriculture as we've known it for millennia, powered by the sun, spread across the land. On the other side, a vision from the future, happening right now. Towering racks of vibrant green, bathed in the cool purple glow of artificial light. This is a vertical farm, a food factory tucked inside a city, where climate is controlled by HVAC systems, and the sun is replaced by LEDs. Two starkly different paths to feeding humanity. One relies on land and logistics, the other on electricity and technology. The question that defines the future of our food system is this: which one is truly more sustainable? As our global population surges towards 10 billion and the pressures on our land, water, and climate intensify, this is not just an academic debate. It's a critical puzzle we must solve. The answer is far from simple, involving a complex trade-off between two of the most fundamental resources of our civilization: energy and land. Traditional agriculture, for all its reliance on the free energy of the sun, comes with enormous hidden costs. The concept of food miles captures just one part of this. A head of lettuce grown in California might travel nearly 3,000 miles to reach a plate in New York. This journey requires refrigerated trucks burning diesel fuel, contributing to greenhouse gas emissions and air pollution. Along the way, a staggering amount of food, up to 40% for some crops, is lost to spoilage before it ever reaches a consumer. It's a system defined by distance, waste, and vulnerability. Vertical farming proposes a radical alternative. By moving food production into the heart of urban centers, it collapses the supply chain from thousands of miles to just a few blocks. Produce can be harvested in the morning and be on a restaurant's menu or a consumer's table by the afternoon. This hyper-local model virtually eliminates transportation emissions and drastically reduces spoilage. But this efficiency comes at a price, paid in kilowatts. To understand the true cost, we need to perform what's known as a life cycle assessment, or LCA, weighing every single input and output. And the biggest input by far is energy. So let's begin our analysis there. Let's begin with the energy of light. In a windowless, multi-story farm, every single photon a plant uses for photosynthesis must be created artificially. This is the single largest energy expenditure in most vertical farms. For decades, this was a non-starter. The inefficiency of older lighting technologies like high-pressure sodium or fluorescent bulbs made indoor farming economically and environmentally unviable. The game changer was the light-emitting diode, or LED. LEDs are semiconductor devices that convert electricity into light with astonishing efficiency. This efficiency is measured in a unit called micromoles per joule. It tells us how many particles of light, or photons, are produced for every joule of electrical energy consumed. Early LEDs were only marginally better than legacy lights, but relentless innovation has led to a Moore's law-like progression. Today's best horticultural LEDs are over 300% more efficient than the lights of just a decade ago, a technological leap that has single-handedly made vertical farming feasible. But it's not just about efficiency, it's about precision. Unlike the sun, which has a fixed daily cycle, LEDs can be controlled completely. This allows farmers to optimize the photo period, the duration of light the plants receive each day. While an outdoor plant is limited to the natural length of a day, an indoor crop of lettuce might be given a 16-hour day and an 8-hour night every single day of the year to maximize its growth rate without causing stress. This precise scheduling ensures no energy is wasted providing light when the plant can't use it effectively. Next, we must consider the intensity of the light. This is measured as the photosynthetic photon flux density, or ppFD. It quantifies the number of photons hitting a square meter of the crop canopy every second. Different plants have different needs. Delicate microgreens might thrive under a gentle ppfd of 150, while a fruiting crop like strawberries might require a much more intense 400 or 500 to produce sweet, juicy berries. Using LEDs, farmers can deliver the exact intensity required, no more, no less, preventing wasted energy from overlighting the crop. Finally, these two concepts, photoperiod and ppfd, combine to give us the most important metric for plant growth, the daily light integral, or DLI. DLI is the total number of photons that land on the crop canopy over a 24-hour period. Think of it as the total volume of light the plant receives each day. Outdoors, DLI is unpredictable. It varies dramatically with season, latitude, and daily weather. A cloudy winter day might provide a DLI of just 5, while a clear summer day could exceed 50. This inconsistency is a major limiting factor in traditional agriculture. In a vertical farm, the DLI is a precision dial. Farmers can calculate the exact DLI a crop needs for optimal growth, say 17 for a head of butter lettuce, and program the lighting system to deliver that exact amount, day in and day out, 365 days a year. This absolute control and consistency is what allows vertical farms to produce crop yields that are hundreds of times higher per square foot than a field. But it all hinges on the massive, continuous, and reliable supply of electricity needed to power the artificial sun. To truly understand the sustainability of vertical farming, we must look past the gleaming racks and into the heart of its energy consumption. This is where the debate truly ignites. The two largest operational costs and the two biggest energy draws are lighting and climate control. Get these right, and a vertical farm can be a model of efficiency. Get them wrong, and it becomes an energy-intensive liability. So, let's break down this energy equation, starting with the most visible component, light. Next up, the energy of light. Unlike a traditional farm, which relies on the free and abundant energy of the sun, a vertical farm must create its own sunlight, 24 hours a day, 365 days a year. This is achieved through light-emitting diodes, or LEDs. The revolution in LED technology is, in many ways, the catalyst that made modern vertical farming viable. Early attempts with fluorescent or high-pressure sodium lamps were simply too inefficient and produced too much heat. Today's horticultural LEDs are marvels of efficiency. They convert electricity into photosynthetically active radiation, the specific wavelengths of light that plants use for growth, with unprecedented precision. We can tune the light recipe, providing more red and blue light, which are crucial for photosynthesis, and less green and yellow light, which plants largely reflect. This spectral tuning means almost no energy is wasted producing light plants can't use. But how much light is enough? This is where we introduce two critical concepts: photosynthetic photon, flux density, or ppfd, and daily light integral, or DLI. Think of ppfd as the intensity of the light, the number of photons landing on a given surface every second. DLI, on the other hand, is the total amount of light delivered over a 24-hour period. It's the combination of intensity, ppfd, and duration, the photoperiod. Different plants have different needs. A head of lettuce might thrive with a DLI of 15 moles per square meter per day, while a fruiting plant, like a strawberry, could require double that. The farmer's goal is to provide the exact DLI a crop needs for optimal growth, without wasting a single photon or a single watt of electricity. By controlling the photoperiod, they can give plants an ideal day every day, often using pulsed lighting or shorter, more intense light cycles to maximize growth while minimizing energy use. But all this light, even from efficient LEDs, produces heat. And that brings us to the second, less visible, but equally critical part of the energy equation. Now, the climate challenge. Every vertical farm is a sealed environment. While this protects crops from pests and weather, it also means that every bit of heat and humidity generated inside stays inside. Managing this internal climate is the job of the HVAC system: heating, ventilation, and air conditioning. And it is a monumental task. The primary challenge is removing waste heat generated by the thousands of LEDs. This is what engineers call the sensible load, the raw heat you can feel. But there's a second, more complex challenge: humidity. Plants are constantly transpiring, releasing water vapor into the air through tiny pores in their leaves called stomata. In a sealed room packed with tens of thousands of plants, this adds an enormous amount of moisture to the air. This is the latent load, and removing it requires dehumidification, which is notoriously energy intensive. If humidity gets too high, it can lead to mold, disease, and poor nutrient uptake. To manage this delicate dance between temperature and humidity, operators focus on a metric called vapor pressure deficit, or VPD. VPD is the difference between the amount of moisture the air can hold when saturated and the actual amount of moisture in the air. It's a direct measure of the drying power of the atmosphere. A low VPD means the air is humid, discouraging transpiration. A high VPD means the air is dry, which can stress the plants. By precisely controlling VPD, farmers can essentially steer the plant's behavior, encouraging it to transpire at a healthy rate to draw up water and nutrients from its roots, but not so much that it becomes stressed. Achieving this perfect VPD requires a constant, energy-hungry balancing act of cooling and dehumidifying. So, when we ask if a vertical farm is sustainable, the answer isn't just about the lights. It's about the complex, interconnected system of light, heat, and humidity. The efficiency of the LEDs, the insulation of the building, the intelligence of the HVAC system, and the specific needs of the crop all converge. The challenge for the future of farming isn't just growing plants, it's mastering the environment in which they grow, 1 watt at a time. Vertical farming has been marketed as the future of food. A clean, controlled urban solution that grows lettuce inside skyscrapers, eliminates pesticides, and delivers produce within hours instead of days. It's a vision of agricultural utopia, where our cities feed themselves with hyper-local, perfectly fresh food, year-round, regardless of the weather outside. But behind the glowing pink LED lights lies the fundamental question that bothers scientists and policymakers. Does vertical farming actually help the climate, or does it simply move emissions from trucks to power plants? Is this a genuine leap forward for sustainability, or a high-tech, energy-intensive distraction from more practical solutions? Today, we break down this debate with a clear, evidence-based lens. We're going to talk about free sunlight versus paid electricity, food miles versus grid dependency, heating and cooling loads, spoilage, biomass efficiency, and the surprising places where vertical farms win big and where they fail the hardest. We'll explore the science of light, the physics of humidity, and the economics of growing food indoors. By the end, you'll understand the precise conditions that make a vertical farm a climate hero, and the conditions that turn it into an energy hog. Let's begin with the core conflict. The core conflict: free sunlight versus paid electricity. Traditional farming uses the greatest free energy source in the universe, the sun. Every day it delivers an immense amount of energy to the Earth's surface, powering photosynthesis for free. Vertical farming replaces that free sunlight with LED panels that must run for 14 to 18 hours per day. To replicate the sun's power, these lights must deliver a specific amount of energy, measured as the daily light integral, or DLI. This requires a high photosynthetic photon flux density, or PPFD, which is essentially the intensity of the light hitting the plants. And it's not just lights. Indoor farms need pumps for nutrient circulation, fans for air movement, sensors for monitoring, and often, the most energy-hungry component of all, massive HVAC systems to control temperature and humidity. A lettuce field outdoors receives sunlight at zero cost. It gets the full spectrum of light, for free, every single day. A vertical farm pays for every photon, every single particle of light that drives photosynthesis, comes with a price tag on the electricity bill. Critics argue this is insanity. Why burn coal or natural gas in a power plant, lose energy in transmission, and then convert that electricity back into a narrow spectrum of light just so that lettuce can grow indoors? Why go to such lengths to replicate a process that nature has already perfected, powered by a giant fusion reactor in the sky? It seems on the surface like a profoundly inefficient way to make food. But then comes the counter-argument: logistics. And this is where the simple energy calculation gets complicated. The logistics argument: energy at the field versus energy at the city. Most food does not travel a few kilometers. It often travels hundreds or even thousands. A head of lettuce grown in California may be eaten in New York. One grown in Spain may end up in Sweden. This journey isn't simple. The transportation chain includes diesel trucks, refrigerated shipping containers, massive refrigerated warehouses, multiple handling centers, and last-mile delivery vans. Each step consumes fuel and energy, adding to the carbon footprint of that single head of lettuce. Vertical farming wipes out that entire chain. By placing the farm directly inside the city it serves, the supply chain is radically shortened. Instead of days or weeks of travel, produce goes from harvest to fork in under 24 hours. No long-haul diesel trucks. No vast, energy-guzzling cold storage warehouses. No crushed leaves from rough handling. No rotten heads of lettuce discarded at the supermarket because they couldn't survive the journey. But the most powerful argument for vertical farms is not just the energy saved on transportation. It is the staggering amount of waste it prevents. The waste factor, the hidden energy nobody talks about. In traditional agriculture, studies show that 30 to 40% of leafy greens are wasted before they ever reach the consumer. They wilt in transport, get damaged during handling, expire on the shelf, or are rejected by retailers for purely cosmetic reasons, a slightly misshapen leaf, a minor blemish. This is a colossal loss of food. A vertical farm delivers produce that is uniform, clean, and harvested just minutes from the point of distribution. It's often sold as living produce with roots intact, extending its shelf life dramatically. Restaurants report near 100% usage, zero washing required, zero trimming of damaged outer leaves, zero spoilage in the walk-in cooler. Waste is energy. Every kilogram of wasted lettuce represents a kilogram that required water, fertilizer, land, labor, and transportation energy, all for nothing. It's embodied energy, thrown directly into the trash. When 40% of the crop is lost, it means 40% of all the resources used to grow and ship it were also wasted. Vertical farms eliminate this waste almost entirely. By producing exactly what is needed, where it's needed, and delivering it in perfect condition, the system becomes radically more efficient. This is where the energy math becomes more interesting. Even if a vertical farm uses more electricity per kilogram of produce, the overall system may still use less total energy per kilogram of produce when waste is factored in. You grow one head of lettuce to eat one head of lettuce. You don't need to grow 1.5 heads to account for spoilage. Fewer inputs, fewer losses, no spoilage buffer. So which one wins? The high electricity use of the farm or the high waste and transport energy of the field? It depends, and a huge part of that dependency is a component that's often overlooked. The HVAC monster, the real energy hog. While LED lights get most of the attention, HVAC, heating, ventilation, and air conditioning, is the real beast. Plants transpire. They release water vapor into the air as a natural part of photosynthesis. In a closed indoor farm with thousands of plants, that humidity builds up incredibly fast. If it's not removed, you create a perfect breeding ground for mold, mildew, and fungi, which can wipe out an entire crop in days. So that humidity must be constantly removed by powerful dehumidifiers. In many vertical farms, especially in warmer climates, HVAC consumes more electricity than the lighting itself. This is because removing humidity is extremely energy intensive. The technology is improving, with new methods like liquid desiccants and energy recovery ventilators. But for now, HVAC remains the Achilles heel of indoor farming's energy budget. This is where climate and geography matter. A vertical farm in a cool, dry climate like Norway, Iceland, or Canada, powered by abundant hydro or geothermal energy, is nearly carbon neutral. The cold outside air can be used for cooling, reducing the HVAC load. But a vertical farm in a hot, humid climate like Florida or Singapore, running on a coal-dominant grid, may emit far more carbon than outdoor farming, plus long-distance trucking combined. The grid determines the sustainability. The grid dependency problem. Vertical farming is not inherently green, it is grid dependent. Its environmental footprint is a direct reflection of the electricity grid it plugs into. If the electricity is clean, generated from solar, wind, hydro, or nuclear, then the farm is clean. Its primary environmental drawback is neutralized. If the electricity is dirty, generated from coal or natural gas, then the farm is dirty. It becomes a concentrated point of consumption for fossil fuels. That makes location everything. A renewable-powered indoor farm becomes a powerful asset for urban resilience and low-carbon food production. A coal-powered indoor farm becomes an environmental liability, trading diesel emissions for smokestack emissions. This is why vertical farms are finding the most success in places like Japan, Singapore, Scandinavia, and the UAE, regions with a combination of strong government incentives, increasingly clean grids, extreme land or water limitations, or a strategic need for food independence. The biomass question, are we growing the right crops? Even with clean energy, vertical farming cannot yet produce our staple carbohydrates at scale. Wheat, rice, corn, potatoes. These are low-value, high-volume crops that form the foundation of our diet. They require immense amounts of energy to produce a kilogram of edible food, making them economically and energetically unfeasible for indoor cultivation today. Instead, indoor farms focus on high-value, fast-growing crops. Leafy greens like lettuce, kale, and arugula. Culinary herbs like basil, cilantro, and mint. Microgreens, which are nutrient-dense and have very short growth cycles. And increasingly, fruits like strawberries. These crops are chosen because they are lightweight, perishable, fragile, and command a high price per kilogram, justifying the higher production cost. Trying to grow wheat indoors would be an energy disaster. The cost of electricity would far exceed the value of the grain. But growing basil indoors? That's a perfect match. It's a fragile herb that ships poorly and has a high market value, making it an ideal candidate for local indoor production. So the real question is not just, is vertical farming good or bad, but rather, are we choosing the right crops for the right system in the right location? The future, hybrid agriculture. The truth is that the future of food is not a battle between outdoor and indoor farming. It's not a zero-sum game where one must replace the other. It is a division of roles, creating a more resilient and efficient hybrid system. Traditional agriculture, with its reliance on free sunlight and vast open spaces, will continue to dominate the production of bulk calories, our grains, tubers, and legumes. Vertical farming will take over the production of fast-decaying greens, high-value herbs, and sensitive specialty crops that benefit from the tight control and proximity to consumers that indoor environments provide. Together, they form a hybrid system where each method plays to its strengths. Outdoor farms provide the scale needed to feed billions. Indoor farms provide precision, quality, and local availability for key produce. The overall length and complexity of our food logistics shrink. Food waste from spoilage and transport collapses. National food security improves by reducing reliance on distant sources. and our cities gain a new layer of resilience against supply chain disruptions. The future is not replacing the field. It is complementing it, creating a smarter, more specialized, and more sustainable food system for everyone. Conclusion. So which side wins in this complex debate? The energy argument against vertical farms or the logistics and waste argument for them? The answer is neither. It's the wrong question. The real winner is the region with the cleanest grid combined with the smartest deployment. The winner is the system that intelligently integrates both farming methods. Vertical farms are incredible tools for sustainability when powered by renewables, located near urban centers, and focused on growing the right crops where they can displace long, wasteful supply chains. They are wasteful exercises in technology when powered by fossil fuels, located in the wrong climate, and used to grow crops that could be sourced more efficiently from a field nearby. The debate is not about LEDs versus sunlight. It is about systems thinking. It's about looking at the entire chain, from seed to plate, and identifying the most efficient path for each type of food. When does vertical farming make sense? When the grid is clean, when post-harvest waste is high, when logistics are long and expensive, when arable land is scarce, when fresh water is scarce, as vertical farms use up to 95% less water, and when food safety and predictability are a top priority. When does it fail? When it's treated as a universal solution for all crops in all regions, regardless of the local energy source, climate, or existing agricultural landscape. It fails when it ignores the elegant efficiency of the sun. This debate is not about food alone. It is about infrastructure, economics, climate science, and the complex interconnected supply chains that underpin modern life. It's about designing a future that is both high-tech and in harmony with natural systems. If we get the mix right, vertical farming becomes a powerful climate hero, strengthening our food security while reducing our environmental impact. If we get it wrong, it becomes just another energy hog, a well-intentioned but ultimately unsustainable venture. The choice, as always, depends on our wisdom to use the right tool for the right job. Thank you for watching Eco Innovatech.